In this example, we're pulling a spool to the right with this force P applied to the end of the cable, which is wrapped around the inner radius of the spool. We know that the spool moves in a way that it rolls without slipping. The center of the spool is moving to the left with some initial speed, and what we want to do is find the angular velocity of the spool after 10 seconds in time. So we're looking for a change in velocity, angular velocity, in terms of time. So we're going to use the angular impulse momentum equation. So let's look at the forces. We've got this force P acting on the end of the cord. We have a weight of mg. We have a normal force in, and we have a friction force F. Both of these acting at the no-slip contact point of C. Here I'm going to do a moment about the contact point C. That's a valid point to use because if we were using Newton-Euler equation for no slip, that would be an appropriate one to use and still have summation of moments equal to I alpha. We use the same rule here. So if I do a summation of moments about O, then F and N don't cause a moment about C, nor does the weight. All we've got here is the applied force P. It's got a moment arm of R minus R. It's in the minus K. I guess I should say, remind ourselves X and Y are given as that. So therefore, if I integrate minus P R minus R in time, gives me the mass moment of inertia at C times omega 2 minus omega 1. And keep in mind that IC is the mass moment of inertia about C, and we're given mass moment of inertia in terms of what it is about G, which is the same thing here as point O. So we'll say that IC is equal to IO plus M big R squared. So that'll be KO squared plus R squared times M. So we can obviously bring the constant minus R on the outside, integrate P in time, P dt. And let's see, P is equal to 1.5 times T. From 1 to 2. So the left-hand side becomes minus R, 1.5 divided by 2 T squared, so it's just going to be T2 squared is that. Now for kinematics, we might know the answer, but let's go through it in detail here so we can be sure to get the correct sign. So the velocity of point O, we'll say, is equal to velocity of the contact point, no slip, plus omega crossed R O with respect to C. C is a no slip point. So in general we have omega K crossed with a vector from C to O, which is a plus RJ. So this becomes a minus R omega I. So therefore, omega 1 is equal to the the negative of VO1 divided by R. And keep in mind that since O is moving initially to the left, we need to put a minus 3 in for there. So this is going to be a plus 3 over R. So in the end, when we solve this, we see that omega 2 is equal to omega 1 minus the quantity R minus R, 1.5 divided by 2 T2 squared. Like that. And be sure that when you put in your numerical value for omega 1, you put in a plus 3 over R. So what do we do? Well, we begin with a free body diagram of the spool. Recognize that C is a no slip point, so I'm going to do my moments about C, and that gives me the angular impulse momentum equation as this. We need to do a little bit of kinematics in order to find out what omega 1 is, and since the spool is initially moving to the left, that actually gave us a plus, a counterclockwise direction there for omega 1. Substitute that into our angular impulse momentum equation, and we get omega 2.